Section 5.4 gives us the fundamental theorem of calculus in all its glory. We've already seen the second part in 5.3 that relates the definite integral to antiderivatives, but part 1 of the fundamental theorem has to do with this accumulation function, which basically says if I'm looking at integrals, definite integrals, the area from a to, I don't know, say x, I can think of x as a variable, where if I slide it and move it around, I'm talking about accumulating area from a fixed number to some other point. And when I range that some other point, when I vary it, because it's a variable, I get a new function called g of x. Why would I want to do that? The interesting thing here is that the derivative of this function, and the function is kind of an integral, the derivative of the integral of f is f itself, the integrand. It comes back to the integrand. And so problems that ask us to use the fundamental theorem of calculus part 1, really, we're just finding the right way to spit out this integrand as an answer without doing any anti-differentiating. Okay, so one of the most important things to notice about the way this is stated is that this upper bound of the integral, the definite integral, has to match exactly the variable of the accumulation function. You see here this is an x and this is an x. Well, in our problem, you have the variable as x, but the upper bound of integration is 1 over x. It's a function where instead of finding a variable where I expect it, I find a function of that variable where I expect it. And so that ought to remind us of the chain rule from calculus. So this problem is really similar to example 5 from the textbook, and we're going to use the fundamental theorem of calculus part 1 along with the chain rule to solve it. So recall the chain rule. What was that from calculus? Here I've got it written in Leibniz notation, but essentially you're going to think of the function that you're trying to take the derivative of as having an outside and an inside. It's a composite function. And so in order to take the derivative of the whole thing, you take the derivative of the outside function and you leave the inside alone, so derivative of the outside with respect to the inside, and then you come back and you multiply by the derivative of the inside function, and that's with respect to the original variable. So what does that mean in the context of our problem? We want to take the derivative of h of x in our problem with respect to its variable, which is x. So the chain rule of that would be dh dx equals dh du times du dx. That's just rewriting the chain rule in terms of the variables given to us in our problem. Now, our variables also don't exactly match the variables in the statement of the fundamental theorem. So let's come back and rewrite the statement of the fundamental theorem in terms of our variables. So I've got here this function, the integrand is arctan t dt, and the upper bound of integration, I'm going to let that be u, because that's my inside function. I don't like it being a function, so I'm going to use the variable u to represent it. And a can be any number, in our case it's 2. And now instead of g of x here, they called it h already, so let's call it h. It's a function of u, because we want the variable to be the one that's represented as the upper bound of this integration. So the fundamental theorem tells us once I have it written this way, where the u's match, the variables match, then the derivative of that accumulation function, see here g prime, the derivative of our h, dh du, is equal to the integrand where we plug in the variable. And here my variable is u, my integrand is arctan t, so I have that the derivative of h with respect to u is arctan u. This is what the fundamental theorem gives us. To solve my original problem where I want dh dx, in addition to dh du, I'm also going to need to find du dx. So here, what was u? U was 1 over x. Rewriting, that could be x to the negative 1. So the derivative of that, and that's just a power rule. Bring down your negative 1 to the front, so I have a negative, and the power goes down by 1, so negative 2 in the derivative. The derivative du dx is negative 1 over x squared. So we put these together, and I get that dh dx is dh du times du dx. dh du up here was arctan u, and du dx is negative 1 over x squared. And then, of course, we don't want to leave our answer in terms of u, so I go in and plug back in that u is 1 over x, and I just flip-flop the order because I like to see this fraction in front of the arctan. And we're done. But I'll admit that my answer doesn't look like the way the book worked out example 5. So if I wanted to write the same solution differently, just kind of saying it in different symbols, same words, different symbols, I can talk about the derivative of the whole thing, the composite function, equals the derivative of the outside function with respect to u, that leaving the inside function alone, here, see the u's match, times the derivative of the inside function with respect to the original variable. So this is by the chain rule. This is what allows us to write it out this way, and I'm letting u equal 1 over x in order to do so. In this case, the fundamental theorem of calculus part 1 applies just to this little spot right here, this part, and it tells us that the derivative of the definite integral is the integrand evaluated at the variable, which is u here, so arctan u, and then times du dx. I haven't handled that part yet. And then I go and I finish everything up and plug in my 1 over x for u, and of course du dx I already figured out up here is still negative 1 over x squared. So that's my final answer, same as the final answer we got up here. They match, and two different ways of writing up the same work in a problem. Thanks.